Welcome to my channel Chem Time. Good evening. Welcome to my presentation. Today I am going to discuss heat exchanger design and the principal methods that are used for heat exchanger design. I start the presentation by highlighting the significance of today, May 9th, where Mr. Michael Levitt was born on 9th May 1947, and he is the recipient of Nobel Prize in the year 2013 for his contribution on developing accurate computer models for chemical reactions. Coming to today's presentation on heat exchanger design, there are two principal methods that are being used for heat exchanger design. One is NTU method and the second one is logarithmic mean temperature difference method. And this presentation is useful to chemical, mechanical and agriculture engineering students. I am going to start my presentation with NTU method and the highlights, the important factors related to the logarithmic mean temperature difference is discussed in my previous presentations, and those presentations can be used to calculate the heat transfer area, which I have given two problems, and those two problems can be solved using my videos for the heat transfer area. To start with, I'm going to discuss the NTU method, that is number of transfer units method. This method is useful when we want to determine the outlet temperature of hot as well as cold fluid, provided the inlet temperature of hot as well as cold fluid is given. We define a parameter called effectiveness factor, and this is defined as the ratio of actual heat transfer rate by maximum heat transfer rate. This equation is familiar to all mechanical, chemical and agriculture engineering students when they carry out the laboratory experiments on effectiveness of counterflow and parallel flow heat exchanger. The maximum heat transfer is calculated based on the lowest value of capacity rate. The capacity rate is defined as mass flow rate into the specific heat. And we need to consider the lowest value of capacity rate between the hot and cold fluid. And the second one is we need to consider the highest temperature difference. And the highest temperature difference is possible between the inlet of hot fluid and the inlet of cold fluid. So, knowing the effectiveness, the actual heat transfer rate can be calculated. This is explained through the following problem. Consider a countercurrent flow heat exchanger with inlet temperature of two fluids, 300 Kelvin and 350 Kelvin. The heat capacity rates of two fluids are 1000 watts per Kelvin and 400 watts per Kelvin, and the effectiveness of heat exchanger is 0.5. The actual heat transfer rate is. This is the problem given in GATE 2023 for mechanical engineering students. The maximum temperature difference is, as I mentioned earlier, is the temperature difference between hot fluid inlet and cold fluid inlet. That is 350 minus 300, that is 50 Kelvin. If you look at carefully, I am not writing degree Kelvin. I am just writing Kelvin. I request all the viewers to look at this carefully, and possible reason for writing K only, I request all of you to mention in the comment box. The heat capacity rates given are C1 is 1000 watts per Kelvin and C2 is 400 watts per Kelvin. So the lowest of these two values is C2, that is 400 watts per Kelvin. So Qmax can be calculated as C2 into delta T max, that is 400 watts per Kelvin into 50 Kelvin. And I suggest all of you to write the units for any item which need to be put in the calculations, because this gives you the correct picture of the final unit which we are going to get. So with epsilon is equal to 0.5 and Qmax is equal to 20,000 watts, equation 1 boils down to 0.5 is equal to Q by 20,000 watts and Q is 10,000 watts. 1000 watt is 1 kilowatt, so Q is 10 kilowatts. But I'm not stopping the problem. As far as the GATE examination for mechanical engineering is concerned, this is enough. But As we have been saying all the while that NTU method is used for measuring the outlet temperature of hot fluid. So THN minus TH out is equal to Q by MC of hot fluid, where THN is the inlet temperature of hot fluid and TH out is the outlet temperature of hot fluid, is equal to Q, that is the actual heat transfer rate, by MC of hot fluid. So 350 minus TH out is equal to 10,000 watts by 1000 watts per kilowatt, that is 10 kilowatts. So TH out is 340 kilowatts. The outlet temperature of cold fluid is TC out minus TC in is equal to Q by MC cold fluid. With TC in at 300, TC out can be calculated as 325 Kelvin. This is one problem given in mechanical engineering gate examination in 2003. The second problem, where normally we mentioned earlier that NTU used for calculating the outlet temperatures, but in this particular problem, all the temperatures are given and we are asked to calculate the NTU, that is number of transfer units. This is the problem. A perfectly insulated concentric tube countercurrent heat exchanger is used to cool lubricating oil using water as a coolant, as shown in the figure. The oil enters outer annulus at mass flow rate of 2 kg per second and a temperature of 100 degrees centigrade and leaves at 40. Water enters the inner tube at 1 kg per second mass flow rate and a temperature of 20 degrees centigrade and leaves at 80 degrees centigrade. The oil specific heat is 2089 joules per kg Kelvin and that of water is 4178 joules per kg Kelvin. There is no force change between the streams. Under steady state conditions, we need to calculate the number of heat transfer units, and this is the diagram. If you look at the diagram, the temperature difference on each side, that is the 40 minus 20, that is 20, and 100 minus 80, that is also 20. So you cannot use logarithmic mean temperature difference when calculating the LMT. You have to go by arithmetic mean only. And NTU is defined as U into A by C minimum. Normally, in case of problems related to NTU, the heat transfer overall heat transfer coefficient and A, the heat transfer area, are given, and we need to calculate C minimum and calculate NTU. But in this particular problem, U and A are not given. Instead, the temperatures are given, which can be used to calculate UA. UA can be calculated as Q is equal to U into A into, here it is delta T average. Remember, it is delta T average. So as a result, UA will be Q by delta T average. So Q is calculated either for the hot fluid or for the cold fluid. So now the equation boils down to NTU is equal to Q by delta T average into C minimum. So we need to focus on C minimum, and C minimum is calculated as mass flow rate of the hot fluid into specific heat of hot fluid, or mass flow rate of cold fluid into specific heat of cold fluid, and we have to compare these two values to obtain the lowest value. So for hot fluid, the heat capacity rate is 2 kg per second into 2089 joules per kg Kelvin, that is 4178 watts per Kelvin, and for cold fluid it is 1 kg per second into 4178 joules per kg Kelvin, that is 417. Surprisingly, the heat capacity rate for hot fluid is same as the heat fluid capacity rate for cold fluid, so we can take anything as minimum. So delta T average is 20 and C minimum is 4178, and hot fluid is entering at 400 and leaving at 40 degrees centigrade, and its heat capacity is 2089 joules per kg Kelvin. With this, when you substitute all these C values in equation 4, we get NTU is equal to 3. Now, based on LMTD method, we are giving two problems which are asked in gate examination. These two problems are shown below. One is hot oil at 110 degrees centigrade heats water from 30 degrees centigrade to 70 degrees centigrade in a countercurrent double pipe heat exchanger. The flow rates of water and oil are 50 kg per minute and 100 kg per minute respectively, and their specific heats are 4.2 kilojoules per kg Kelvin and 2 kilojoules per kg Kelvin respectively. Assuming the heat exchanger is operating at steady state, if the overall heat transfer quotient is 2000 watts per meter square degree centigrade, calculate the heat transfer area. I request all the viewers to post the answer in the comment box for this problem. And the next problem is hot water is cooled from 450 Kelvin to 350 Kelvin using cold water at 300 Kelvin. And this is done in a countercurrent 1-1 heat exchanger. The flow rates of hot water and cold water are 1 kg per second and 5 kg per second over the temperature. And over the temperature range, the specific heat of water can be assumed to be constant at 4.2 kilojoules per kg Kelvin. Assuming the heat exchanger is at steady state and if the overall heat transfer quotient is 6000 watts per meter square degree centigrade, what is the heat exchanger area? For this problem also, I request all the viewers to post the answer in the comment box. Now, so far, the discussion is on 1-1 heat exchanger and what happens if the number of passes on the shell side is increased or the number of passes on the tube side is increased. This needs graphical solutions, and my next video will be focusing on these graphical solutions. Thank you one and all. Request you to like, share and subscribe my channel.